Imagine turning on a machine for a test run and accidentally making a discovery that would normally take months. That is exactly what happened on a remote mountaintop in Chile. In a mere 10 hours of preliminary testing, a single telescope identified over 2,000 asteroids that humanity had never seen before. If you have been waiting for the next great leap in our understanding of the cosmos, stop waiting. It has already begun. For as long as humans have looked up, astronomy has been about selection. A scientist chooses a target, a specific star, a curious galaxy, a patch of darkness, and points a telescope at it. It is a precise and inherently narrow process, but astronomers have dreamed of something different. They wanted a device that behaved less like a traditional telescope and more like a celestial surveillance camera, bolted to the bedrock of the world, scanning, logging, and repeating without ever blinking. That dream is no longer just a concept on paper. It has a name. This is Vera C. Rubin Observatory, and its first light has finally arrived. The facility stands atop Cerro Pacuan, a jagged peak in the Chilean Atacama Desert, rising roughly 2,682 meters above sea level. This is sacred ground for astronomy. The air here is impossibly dry, and the nights are so clear they feel almost unnatural. The Rubin Observatory isn't alone up there. It shares the ridge with giants like the Gemini South Observatory and the Southern Astrophysical Research Telescope. Yet, despite the neighborhood, Rubin is fundamentally different in both its philosophy and its architecture. It wasn't built by a single space agency like NASA. It is a massive collaboration, a partnership between the U.S. National Science Foundation and the Department of Energy, managed by a coalition of universities and supported by international partners. It is the result of over 3 decades of planning, engineering, and construction that formally kicked off in 2015. At the core of this facility sits the Simon E. Survey Telescope. When completed, it became the 7th largest telescope on Earth. Its primary mirror spans a staggering 8.4 meters, significantly wider than the mirror inside the Hubble Space Telescope. But size isn't its only trick. Most telescopes rely on 2 mirrors to gather and focus light. The Simon E uses 3, an 8.4 meter primary, a 3.5 meter secondary, and a 5 meter tertiary. This unique 3-mirror design is the secret sauce. It allows for an extraordinarily wide, flat field of view covering roughly 9.6 square degrees of the sky. To put that into perspective, if you look at the full moon, you are seeing about half a degree of sky. The Rubin Observatory sees an area equivalent to 45 full moons in a single snapshot. That is not a figure of speech, that is the actual optical reality. And that wide angle is the foundation for everything this observatory is about to achieve. Attached to the back of this optical beast is a device that shattered records before it even took its first real picture. Known as the LSST camera, it is roughly the size of a small car, 3 meters long, 1.6 meters wide, and weighing nearly 3 metric tons. This is the largest digital camera ever constructed for astronomy. Not just currently, but ever. Its film is a focal plane made of 189 individual sensors stitched together so perfectly that they function as a single imaging surface. The resolution? 3.2 billion pixels. That's 3,200 megapixels per shot. If you wanted to display just one full-resolution image from this camera, you wouldn't be able to do it on your computer monitor. You wouldn't even be able to do it on a giant TV. You would need 385 4K ultra-high-definition screens arranged side by side just to show one picture. Because this sensor array is so sensitive, it operates at cryogenic temperatures. A specially designed cooling system keeps the electronics stable, preventing the heat of the camera itself from creating noise that would corrupt the data. The camera is designed to cycle through 6 different filters, from ultraviolet to near-infrared, and snap a massive wide-field image every 30 seconds. Then the telescope moves slightly, and it does it again and again. All night long, every clear night, for a decade. When you combine a 3.2 gigapixel camera with a cadence of 1 image every 30 seconds, the amount of data you generate becomes hard to comprehend. Rubin will produce approximately 20 terabytes of raw data every single night. Let's compare that to the space telescopes we know and love. The Hubble Space Telescope generates about 8 terabytes of data in a year. The James Webb Space Telescope, the most advanced observatory in orbit, collects around 200 terabytes annually. Rubin, operating from the ground, will outpace Hubble's yearly output in a single night by a factor of 2. Over its 10-year mission, the survey is projected to amass 500 petabytes of data. that is 500,000 terabytes, containing measurements of billions of celestial objects. The volume is so immense that they couldn't just use standard internet lines. A dedicated 100 gigabit fiber optic connection was laid specifically to blast this data from the Chilean mountaintop to a processing center in the United States. This brings us to a critical point. No human being nor any team of humans could ever look through this much data. Without artificial intelligence, this observatory would be useless. The data flows into a processing pipeline powered by machine learning. The system is designed to perform difference imaging. Essentially, the AI takes the new image from tonight and compares it to a template, a reference image of what that part of the sky looked like before. It then subtracts one from the other. If nothing has changed, the result is a blank screen. But if something has moved, brightened, dimmed, or appeared out of nowhere, it gets flagged. This mechanism allows Rubin to detect an estimated 10 million transient events every night. We are talking about supernovae exploding, asteroids drifting through the frame, variable stars pulsing, or black holes flaring up in distant galaxies. The system generates alerts in real time, sending coordinates to other observatories around the world within 60 seconds, allowing them to swing their telescopes and catch the action before it fades. Now, let's talk about the images. The first release from the observatory, taken during its commissioning phase in early 2025, has already proven that the machine works better than anyone dared to hope. The headline image is a mosaic the team calls the Cosmic Treasure Chest. It is a composite of over 1,000 individual exposures taken over 7 nights, covering a patch of sky in the Virgo cluster. When you first look at it, you see bright spiked stars. These are foreground objects, stars within our own Milky Way. They are so bright compared to the background that their light bends around the telescope's support struts, creating those cross-shaped spikes. But look past them. Behind those local stars lies a staggering tapestry of approximately 10 million galaxies. Let that sink in, not 10 million stars. 10 million galaxies, each one containing billions of stars of its own, each one a universe unto itself. And all of this was captured in a mosaic that covers just a tiny fraction of what Rubin will eventually survey. Zooming into the upper left of this image reveals a tale of cosmic aging. First, we see Messier 49, a colossal elliptical galaxy. It glows with a soft, warm yellow light. In the world of astrophysics, elliptical galaxies are like retirement communities. They are filled with old, cool stars, reds and yellows, that formed billions of years ago. Messier 49 is quiet. It stopped making new stars eons ago. Its glow is the light of history. But right next to it sits NGC 4535, and the contrast is violent. While M49 glows amber, NGC 4535 blazes with blue and white. It is a spiral galaxy, and it is alive with activity. The blue light comes from massive, hot young stars that are being born right now. Blue is the color of cosmic youth, of energy of stellar nurseries working overtime. These two galaxies appear in the same frame, not because they are neighbors in space, they are separated by vast distances, but because Rubin's field of view is so incredibly wide that objects which used to require separate observations now fit into a single picture. Scan further across the mosaic and you find something even more dramatic, a triple galaxy merger. 3 galaxies, which were once distinct spiral or elliptical shapes, are being torn apart by each other's gravity. You can see the wreckage, stars and gas stretched into long tidal tails, bridges of light connecting the bodies as they spiral inward. It is a slow-motion car crash on a galactic scale. Mergers like this are how galaxies evolve. Even our own Milky Way is a cannibal. It has eaten smaller galaxies in the past and is currently on a collision course with Andromeda. But catching a triple merger in this level of detail from a ground-based telescope is rare. It captures a specific moment in a billion-year process where gravity reshapes the identity of the cosmos. Just below this collision, there is a visual trick. 2 spiral galaxies appear to be sitting side by side like a pair of dancers, but this is a lie of perspective. One is 20 million light-years farther away than the other. They have no connection. They just happen to line up from Earth's point of view. It serves as a reminder that a 2D image of a 3D universe can be deceptive if you don't know how to read the depth. But perhaps the most profound part of this image isn't the giant galaxies. It is the background. Zoom into the darker regions and you see faint, reddish smudges. These are galaxies far beyond the Virgo cluster, some over 1 billion light-years away. Their light began its journey when life on Earth was just moving beyond single-celled organisms. There are millions of them in this image. Many have never been cataloged. They have no names. They are not in any database. Until this camera opened its shutter, they were effectively invisible to us. Now they are data, waiting to be understood. While the galaxies provide the awe, the streaks in the images provide the utility. In the raw data, before the final images were cleaned up, the frames were cut through with diagonal lines. These are asteroids, rocks drifting through our own solar system, caught moving during the long exposures. In just those first 10 hours of testing, Rubin found over 2,000 previously unknown asteroids. This brings us to one of the observatory's most critical missions, planetary defense. Currently, we have tracked about 40% of the near-Earth objects, NEOs, large enough to cause regional devastation. The other 60%, we don't know where they are. We got a grim reminder of this in 2013, when a 20-meter rock exploded over Chelyabinsk, Russia. It released 30 times the energy of the Hiroshima bomb, shattering windows and injuring over 1,600 people. Nobody saw it coming. It wasn't on any map. It just appeared out of the sun and detonated. Rubin is the answer to the Chelyabinsk problem. It is designed to systematically catalog millions of solar system objects over the next decade. This includes everything from city-killer asteroids to comets, and perhaps even the elusive Planet 9 that some theorists believe is hiding in the frozen dark beyond Neptune. The key here is time. If you find an asteroid 10 years before it hits Earth, you can deflect it. It is a solvable physics problem. If you find it 2 days before impact, you can't do anything but brace for impact. Rubin buys us the one thing we can't manufacture: warning time. The second major image release takes us closer to home, into the heart of the Milky Way. This is a combined mosaic of the Lagoon Nebula and the Trifid Nebula. To the naked eye, the Lagoon Nebula is a faint gray smudge in the constellation Sagittarius. Through Rubin's eye, it is a psychedelic storm of gas and dust. The camera captures ultraviolet, optical, and near-infrared light simultaneously. We see the blue burn of massive young stars and the red glow of cool dust. Comparing this to the Hubble Space Telescope is fascinating. Hubble's famous image of the Lagoon Nebula is a masterpiece of detail, sharp, layered, iconic. But Hubble's image covers a tiny keyhole, about 4 light-years across. The actual nebula is 55 light-years wide. Rubin captures the whole thing, plus the Trifid Nebula above it, plus star clusters below it. Hubble sees the detail of a single leaf. Rubin sees the forest. In any given exposure, Rubin photographs 4,000 times as much sky as Hubble. It is a different category of instrument entirely. It is fitting that a machine designed to reveal the invisible is named after Vera Cooper Rubin. In the 1970s, Vera Rubin was studying the rotation of spiral galaxies. According to the physics of the time, specifically Newtonian gravity, stars on the outer edges of a galaxy should move slower than stars near the center, much like Pluto moves slower than Mercury. But that's not what she found. She discovered that the outer stars were moving just as fast, sometimes faster. By all known laws of physics, these galaxies should have flown apart. There wasn't enough visible mass to hold them together. She concluded that there must be a vast amount of invisible matter providing the extra gravity needed to keep the stars in check. She called it missing mass. Today, we call it dark matter. Vera Rubin provided the observational evidence that solidified dark matter as a cornerstone of modern cosmology. She never received the Nobel Prize, an omission that many in the scientific community consider a historic mistake. She passed away in 2016, but in 2019, this observatory was named in her honor, and the connection is more than just a tribute. One of the observatory's primary goals is to map dark matter. How do you map something you can't see? You use gravity. When light from a distant galaxy travels toward Earth, it has to pass by massive objects, galaxy clusters or clumps of dark matter. The gravity of these objects bends the path of the light, slightly distorting the shape of the background galaxy. This is called gravitational lensing. Rubin's camera is so precise that it can measure these tiny distortions across billions of galaxies. By analyzing how the background images are warped, astronomers can reverse engineer the location and density of the dark matter that caused the warping. Over 10 years, Rubin will build a 3D map of dark matter across the entire observable universe. Vera Rubin discovered the existence of this invisible substance with a spectrograph and a notebook. The observatory bearing her name will chart its structure with a 3.2 billion pixel camera and 500 petabytes of data. Perhaps the most radical thing about the Rubin Observatory isn't the hardware or the science goals, it's the policy. For centuries, astronomy was exclusive. If you wanted data, you needed to be a professional at a major institution with telescope time. Rubin changes that. In a move that will democratize the field, all of the data will be public. The images, the catalogs, the alerts, it's all going online. A professional astronomer at Harvard will have access to the same data as a graduate student in a developing nation or a citizen scientist in their living room. This means that the next great discovery might not come from a professor. It might come from a teenager writing code in their bedroom, or an AI trained by a hobbyist to look for patterns that the professionals missed. We are crowdsourcing the universe. We are witnessing the end of static astronomy and the birth of time-lapse astronomy. The Sloan Digital Sky Survey, which was the previous gold standard, took 20 years to map 35% of the sky. Rubin will do that every 3 days, and then it will do it again and again. By watching the sky change over time, we will see the universe breathe. We will watch stars pulse, supernovae fade, and asteroids drift. We will see the mechanics of the cosmos in motion. These first images, the 10 million galaxies in the treasure chest, the 2,000 new asteroids, are just the warm-up act. They are the proof of concept. The real survey hasn't even started yet. The universe has always been a dynamic, violent, evolving place. Galaxies have always been colliding. Rocks have always been flying past Earth. We just lack the tools to see it happening in real time. Now, on a lonely peak in the Chilean desert, the eye is open. It's awake, and it isn't going to blink for the next 10 years. What will it find? It might find Planet 9. It might spot the next asteroid headed for Earth. It might break our understanding of physics, or it might show us something we haven't even imagined yet. Because that is what happens when you stop looking at one thing at a time and decide to look at everything at once. What blows your mind the most? Is it the 10 million galaxies in a single picture, the detection of 2,000 asteroids in just 10 hours, or the fact that all this data will be free for anyone to explore? Let me know in the comments. And make sure you are subscribed, because as the Rubin Observatory ramps up, the discoveries are going to come fast, and you won't want to miss what comes next.